Hello everyone, what we have is Dr. Ford's Exam 3 equation sheet. I'm going to walk through it and outline what is on it and where it is. It's broken down into sections and he rarely ever labels anything, which doesn't help. It is missing a few equations here and there on top of everything else, but it's always that way. He does kind of break it down by chapter though, but not well. In fact, there are a few things out of place here and there too. Okay, we start up here at the top. I'm going to go ahead and zoom this a little bit, and we're going to walk down it with it zoomed because I think that's easier for everyone to do. Up here at the top, right here, that's an equation that will be used. It's relating the electric field to the magnetic field, and that equation allows you to convert back and forth between them. This one right here is the equation for the speed of light, which you probably will never use. You need to know that is the speed of light, but you probably won't use that. This right here shows up sometimes. What he'll do is ask for what is the longest wavelength, and then he gives you frequency. So you'll have to convert between wavelength and frequency. That's what that one's for. These two you don't really use much. That's angular frequency, and that's like a spring constant or something. And it's not anything you're going to use here in optics. These equations right here, I have never used in the 10 or 15 years I've been tutoring this class. That doesn't mean you won't use them at one point or another, but I've not seen him use them. They're the basic wave equations, and they talk about, that's why the K and the omega are here. They give the frequency and they give the displacement of the wave. Again, he doesn't even use it in Physics 1 with sound, even those equations exist in Physics 1. All right, these two equations right here, they're energy density. I'm just writing no by these in. Those are energy density. Now, these over here are total energy density. And this is also a total. One thing to watch for is Dr. Ford's done these problems wrong for years, and he doesn't use these over here, so I'm going to scribble them out. He almost always uses these for energy density. Okay, now below it over here, we have intensity. And this is reinforcing. Notice what he's using right here. He's using that same equation right here. So he's been using this as intensity for a long time. Okay? And the intensity equation here is missing a little bit. Intensity, and I don't see it on there anywhere, but intensity I is power over area. And he has used that occasionally on a problem set or two. So be aware that that's what intensity is. This over here is radiation pressure. Okay, it's giving the pressure felt on an object due to light reflecting or being absorbed. The P is pressure, okay? The I is intensity. That's why they're next to each other. The C is speed of light, okay? And just remember there is an equation, ICU, I equals CU, which will change these equations up quite a bit. If you put ICU here, pressure just becomes U. If you put ICU here, pressure becomes 2U. Okay? This one right here is the equation for index of refraction. You do need to know that one. That one does show up sometimes. This one is for the wavelength in a film. Okay? Index refraction. Over here, this is Snell's law, which I probably misspelled, but I'm not a big one on laws. This is Malice's law. And this one at the end is Brewster's. Okay? So there you have the first part broken down. Now we start getting into optics with this next set. Okay? Now, with optics, I don't like following the notations he does. I like putting DO, which is S, and DI, which is S prime. Then all my equations look a lot happier. Okay? In other words, if I do that, then this section of equations, and I'm going to go to a fresh page because that one got pretty written up on. This right here ends up being different. It's 1 over DO plus 1 over DI equals F. 1 over F. And I like that better because the O and the I tell me an object and image. Okay? And this continues on through. Like, the thin lens equation is the exact same thing as the mirror equation. So it's 1 over DO plus 1 over DI equals 1 over F. Now, the other thing I don't like that he does, here he has NA and NB. Well, NA I like to call N1, and B I like to call N2. Now, the reason for that is light starts in 1 and ends in 2. So if I'm looking at fish in the water, the light starts with fish and goes to my eye. So we would use the index refraction for water first as 1, and the index refraction of air is 2. Okay? So I don't like his notations on all these. This one over here is for rods. It's for rod with a spherical end. That, I'm not sure what that is. It's magnification of some kind, but I'm not sure what that is. This is what I call DI over DO. So M is negative DI over DO, which is equal to HI over HO. And I don't use this. I use this down here in place of it. Okay? This is the lens maker's equation. Okay? And you have to be careful what R1 and R2 is. R1 is the first one and R2 is the second, just like the ends. And be careful of the signs on the radius because that will get you. Okay, that will really get you pretty quickly if you're not careful. All right, then I forgot this one up here is for the focal length of a mirror. It's half the radius. All right, over here we get optical instruments. Okay, we have the magnifying glass, which, yeah, that's pretty much what that is. This is a microscope. Now, in both the microscope and telescope, F1 is FO, F2 is FE, where O is objective, E is the eyepiece. We are missing equations for the microscope and telescope for the length. The length of the telescope is FO plus FE. I want to say the length of the microscope is FO plus 25. Okay, I'm not sure on that one because I'm going off memory. All right, now down here we get to interference. So, yet again, I came prepared. We have a new one. Okay, and this is the last bit of this equation sheet stuff. All right, this right here, these two, are his way of doing constructive and destructive with radio towers. Okay, this one's here the destructive, this one's the constructive. All right, now right below it we have, and I do this very differently in him, these equations and these equations are pretty much the same. The way it's written, I want to say this is a single slit and this is multiple. All right. Now, I don't really make a distinction between them. Instead of A, I just use D in both. D is the distant width of the slit for a single. It's the distance between slits for multiple. And you have to know when you have constructive and destructive, and they flip-flop back and forth. So you have to be really careful which one you're dealing with. Okay? like on a multiple slit or a double slit, this one right here is constructive, and this one's destructive. Okay, while on a single slit, this would be destructive, and this one's constructive. All right. Now these right here are soap bubbles versus films. Okay. Now they flip back and forth on which one's constructive and destructive, depending on if it's a soap bubble or a film. Okay. And I'm not going to label these out right now. Just know that they are for soap bubbles and films. And the very last one on here, this one down here at the bottom, this is resolving power. This is for being in a plane and looking at cars on the ground. And all the equations circled in red, you also have tan theta is y over x. And that does include this one. Okay? Because when you're looking at the resolving power, what you have is you have your y here, your x here, your theta here, and y is the distance between the objects. X is your elevation. Okay? And that's equal to this. And remember, with the soap film, you have to do lambda film. Resolving power, you have to do lambda film, which is given way up here as that equation there. Okay? Well, there you go. There's a walkthrough. I hope you enjoyed and found this helpful. I will see about getting the sheets I wrote all over posted somewhere so you can print them and see them. And I hope you find it helpful. Thanks, and have a good one.